So today I'll be doing a lecture on introductory algebra. In this lecture, I'll mostly be covering topics that will come out in the AMC 8 up till the AMC 10, although at the very end, we will be solving a challenge question that integrates everything you'll learn today. So to give you guys a brief overview of the contents, first I'll be covering systems of equations, then I'll move on to polynomials and factoring. Now, this might seem like a really limited scope, but actually tons of questions on, well, competition math and specifically the AMC can fit into these three categories. So even gaining a basic understanding on these three topics can help you solve a ton of questions. My goal here in this lecture isn't to help you guys master these subjects, but just to introduce you guys to the basic and most commonly reoccurring themes within these three topics. All right, let's get started. So within systems of equations, the first thing I want to talk about is single variable equations. So as the name suggests, these are equations that only involve one unknown variable. Now, when I say it like that, it sounds deceptively simple, right? Because who can't solve an equation with just one unknown variable? However, these happen to be one of the most common AMC questions, and one of the best ways to improve your score would be to solve these accurately and quickly. These questions often appear as a question that regards time, distance, and speed. So let's look at an example straight away. The 2019 AMC 8 number 16 was, I'll read it out loud. Shane drives 15 miles at an average speed of 30 miles per hour. How many additional miles will he have to drive at 55 miles per hour to average 50 miles per hour for the entire trip? So because this lecture is focused more on the methodologies of solving these questions, I won't give you guys all the time necessary to solve them. I'll just give you guys a moment to read the question and comprehend what exactly it's asking for. And all right, hopefully that's enough time for you guys to have read the question. And so before we get into the solution, you should know that speed equals distance over time. Now, this isn't necessarily a mathematical concept. I suppose it's closer to physics. But if you're solving mathematical questions, you should know this, and you have to know it for this question specifically. So let's let x be the number of additional miles, since that's exactly what we're looking for in this question. Then that would make the total distance 15, because that's what he drives at the start, plus x. And that would make the total time, again, we can use this equation and switch speed and time to find that time equals distance over speed. In that case, it's 15 over 30 plus x over 55. Now then we can set up the equation that speed equals distance over time. Speed, as given in the question as 50 miles per hour, equals distance over time. And so we are done. We're left with a single variable equation that we can solve easily by multiplying and subtracting to yield that x equals 110. A question that may have seemed more difficult initially because it deals with miles and time and distance can actually be solved very easily just by setting up an equation with a single variable. Now, if you think that this is limited simply to the AMC 8, you would be mistaken, because in the second most recent AMC 10, it also appeared at number 6. Since this question is long, I won't be reading it in its entirety, but I'll give you guys another moment just to read it over and again, comprehend what exactly we're looking for and what kind of equation we might need to set up to solve it. And all right, I'll move on to the solution. Again, it's the same process that we did in the previous question. Let's let the total distance be 2d and Gene's speed be x. Again, we have to set up the equation, and this time it's regarding time, since we know they meet at the same time at the halfway point. If we try to set up an equation regarding, say, distance, then it would be much harder because we don't really know how to set up an equation for distance where both sides are equal. However, we know that they meet at the same time, so it's easy to set up an equation where their times are equivalent. And if you read the question properly, then you should understand that it's just d over 4 plus d over 2 plus d over 3. And then if you just simply add these up as fractions, you get 13d over 12 equals d over x, which is how much time Jean will take to get to the halfway point. And that makes the answer pretty obvious, as x equals 12 over 13. So even knowing just how to set up single variable equations can help you solve a lot of questions in the AMC 8 and even early on in the AMC 10, which is why it's so important to get to know how to solve these quickly and accurately. Now, the next thing I want to talk about is linear systems, and these mean when the variables are only raised to the first power. So single variable equations are examples of linear systems, but often linear systems involve more than one variable. So the most common methods for solving would first be Gaussian elimination, which means adding and subtracting between equations to eliminate certain variables. Another common method is substitution, which means you would solve for one of the variables, then you would plug it into other equations. And finally, there's just graphing, where you would find the intersection of the lines defined by the equations themselves. Now, I believe this comes out in school in 8th grade, so hopefully you guys are familiar with these concepts. And again, these appear in the AMC a lot. In the 2019 AMC 10A, now note that this isn't actually a linear equation, but we can use the same strategies that are used for linear equations. It's pretty short, so I'll read it out loud. Anna and Bonita are born on the same date in different years, n years apart. Last year, Anna was 5 times as old as Bonita, and this year Anna's age is the square of Bonita's age. What is n? Again, I'll give you guys just a second to think about it. But really, this is not so much different compared to the two questions we saw before. Let's let Anna's age be A, Bonita's age be B. If we translate this statement into an expression, we find that A minus 1 equals 5 times B minus 1, which we can isolate A or solve for A by saying that A equals 5B minus 4. If we translate this second sentence, let's see, Anna's age is the square of Bonita's age, we find that A equals B squared. Using the substitution method, we find that this and this are the same. So B squared equals 5B minus 4, which helps us set up the quadratic B squared equals B squared minus 5B plus 4 equals 0. And if you either use the quadratic formula or simply factor it, we find that B equals 4 or 1. But since A and B are not equal, they're born in different years. So B can't be 4, which means that B is 4 and A equals 16, giving us that final answer of n equals 12. So for a lot of you guys, these questions may have seemed pretty simple, but as you'll see later, it's essential to know these strategies because they come up in much harder questions as well. It's just that harder questions incorporate a lot of other strategies as well, but you can't ever solve harder questions without knowing these strategies, which is why I wanted to cover them to start this lecture today. All right, moving on to polynomials. So what exactly is a polynomial? Well, it's defined as in one variable as a function p of x, where, as you can see here, a of I is the ith coefficient and an is not 0. So often the leading coefficient, so a sub n, will be equal to 1, in which case it's called a monic polynomial. So just to list some interesting properties, the degree is the number of roots. So for this one, there would be n number of roots. They're not necessarily distinct, they're not necessarily all real, but we know that there are n roots for sure. The factored form would be some number times x minus a times x minus b times x minus c and so on, where a, b, and c are all roots. And if a complex number is one of the roots, its conjugate must be another root. Now, that is to say, if a plus bi is one of the roots, then a minus bi must also be a root. And that's a concept that comes out frequently in competition math as well. There's also Vieta's formulas, which I won't be covering today because honestly, Vieta's formulas could be made into a presentation all on its own. It's such an extensive topic, but it's also a really important topic. So if you're not familiar with it, you should definitely go check it out on your own after this lecture. But really, the point about polynomials is that they're so diverse and flexible that the best way to practice is simply to solve as many questions as possible. There's not a single set way to get really good at polynomial equations, simply because you never know what you're going to run into. Let's see a question from the AMC 8 first. In 2019 AMC 8 number 20 was how many real numbers x satisfy the equation x squared minus 5, parentheses around all of that squared, equals 16. Again, I'll give you guys just a moment to digest the question. And to be honest, this isn't really a traditional polynomial question, but it's about as close as it gets on the AMC 8. Polynomial questions don't appear that much in the AMC 8, but this is a good example of one. So if we get the square root of both sides, we find that x squared minus 5 equals 4 or minus 4. Then if we add 5 to both sides, we get that x squared equals 9 or 1. Finally, getting the square root on both sides yields that x equals plus minus 3 and plus minus 1, which gives us 4 answers. Now, if you really wanted to apply your knowledge of polynomials, you could eliminate answer choice E from the very start. This is a 4th degree polynomial since x squared is squared again. A 4th degree polynomial has 4 distinct solutions maximum, so there's no way that the answer could be 8. So our knowledge of polynomials can come in useful even in questions like this. However, a more common sort of polynomial question would look like this, the 2020 AMC 10A number 17 question. If a function is defined as x minus 1 squared times x minus 2 squared all the way up to x minus 100 squared, how many integers n are there such that p of n is less than or equal to 0? Again, I'll just give you guys a second. But it's important to note that there's a pretty big jump in difficulty from the previous question to this one. That's because polynomial questions, there tend to not be many intermediate level questions. But they're still really important because even if you're at an AMC 8 or early AMC 10 level, you're eventually going to want to solve these. And once you get used to them, once you practice a lot of these, they tend not to be too difficult. And it's the same in the case of this question. Let's look at the solution. So I think the most important step is just to note that there needs to be an odd number of negative numbers multiplied for p of n to be negative. Now what I'm saying is there are 100 pairs of parentheses here. And if this needs to be negative, then there should either only be 1 negative number or 3 negative numbers or 5 negative numbers or so on. There needs to be an odd number of negative numbers. And realizing this helps us get to the solution, to the answer pretty quickly. So 100 numbers make p of n 0. These 100 numbers would be 1 squared, 2 squared, 3 squared, and so on until 100 squared. And then we need to consider the numbers that make p of n actually negative. So every interval between an odd square and an even square works. Now, just to go a bit more specifically into this, if we want one number to be negative, let's say we want just this number to be negative, well, then it should be between 1 and 4. And then if we want 3 numbers to be negative, if you imagine x minus 3 squared and x minus 4 squared over here, then it should be between 3 squared and 4 squared, and so on. So if we get the sum of all of these numbers, the numbers between 1 and 4, numbers between 9 and 6, and so on until the numbers between 99 squared and 100 squared, it should sum to 5,000, and adding 5,000 and 100 gives us 5,100. So as you can see, it's not that we employed a really difficult mathematical concept to solve this question. Rather, it was just our familiarity with polynomials that helped us solve it. So even if you're not necessarily super experienced in math, you can solve these kinds of questions, which is actually a pretty difficult question since it's in the back half of AMC 10. You can solve these kinds of questions simply with your mathematical sense. And as an extension, difficult polynomial questions tend to litter the final parts of AMCs, as to say number 21 through number 25, and they often require some brilliant manipulation or a high level of comfort with complex roots. So if you run into these kinds of questions, I recommend that if you're not here where you can manipulate these polynomials or you're comfortable with complex roots, you really don't need to solve these. And I just looked over the previous 2 years of AMY, well, AMY 1 and AMY 2, And I saw that there were 4 questions, which means these come up pretty frequently, especially in the 2020 AME one, where it came out twice in the second half. So yeah, these questions tend to be pretty difficult. So don't worry too much if you can't solve all of these. And this is just an add-on. One of my personal favorite questions, especially regarding polynomials, is the 2010 AMC 12B number 21. So if you have time after this lecture, you should probably go check it out. It's a really nice solution that can be applied to a lot of other questions as well. But polynomials leads us naturally into factoring, because if we have a polynomial, knowing how to factor it can help us solve it in a lot of cases. But what won't be covered here are general formulas. General formulas for factoring, such as a to the nth power minus b to the nth power, or say a to the third plus b to the third plus c to the third minus 3abc, won't be covered in this lecture. Quite frankly, these just need to be memorized. There's not a lot of strategy involved, and I'm sure you guys can find lists like this where it lists a number of common general formulas that you simply need to memorize. There's no way around memorizing these formulas. But I won't be covering them today because I want to talk more about strategy rather than things you need to know. So I think the first interesting strategy is difference of polynomial squares. Let's look at this question. Factor x to the fourth plus 4. I'll give you guys just a second to think about it again. All right, now I think this question is so jarring because we often anticipate a question like x to the fourth minus 4, which we can do with difference of squares, but we're really not expecting a question like x to the fourth plus 4. But actually, we can solve it by this step. We note that x to the fourth plus 4 is actually x to the fourth plus 4x squared plus 4 minus 4x squared. So we just add 4x squared and subtract 4x squared. Now, what does this give us? This gives us a difference of polynomial squares, because this part is x squared plus 2 squared, and this part is 2x squared. Now, we've got that difference of squares that we wanted from the start, and that helps us factor it out pretty easily. So this is a common strategy, especially if you see a 4th degree polynomial and you don't see any coefficient for x to the 3rd degree or x to the 1st degree. You can find that it's a difference of polynomial squares. So you just need to keep an eye out for the coefficient of the 2nd degree term. Here it's 0, and you should note that's 4 minus 4. All right. Another strategy I want to cover is symmetric polynomials. So again, try factoring x to the fourth minus 3x to the third minus 2x squared minus 3x plus 1. So I underlined these numbers to highlight the symmetry in this polynomial. If it's symmetric around the middle degree, then there's a specific way you can solve this. Now, a lot of you guys might be familiar with it, a lot of you guys might not. But it's useful either way. So I'll be covering it here. And hopefully you guys are ready to go on to the solution. So if we divide everything by x squared, just to emphasize that symmetry, we find x squared minus 3x minus 2 minus 3 over x plus 1 over x squared. Now, this is a pretty symmetry because we have x squared and 1 over x squared. And then we have x and 1 over x. We can capitalize on that symmetry by linking these together, right? We can put these together as x squared plus 1 over x squared. We can put these together as x plus 1 over x. Then we can use that x plus 1 over x squared equals this minus 2 to get this equation. This is all equivalent simply to x plus 1 over x squared minus 3 times x plus 1 over x minus 4. Now, again, this minus 2 turns into this minus 4, because if we square this, then it would be this plus 2. So we'd have to subtract 2. Oh, and this, well, we recognize it as simply a quadratic formula regarding x plus 1 over x, where the roots are 4 and negative 1. So we're done, pretty much. So this simplifies into that. And since we divided everything by x squared at the very start, we multiply x to this, and we multiply x to this to end up with the factored form of x squared minus 4x plus 1 times x squared plus x plus 1. So these two factoring tricks are factoring tricks, hopefully that were new to you. They might not be. But again, these come out often in the AMCs or any type of competition math. So it's important to have these as a basic knowledge as well. All right. So some of you guys may have been sitting here thinking that you already knew all of these things and that you might not be adding on anything new. However, I want to show you guys that you can combine all of these strategies to solve much harder questions. For example, let's look at the 2015 AME number 10. So since it's number 10 on an AME, this is very difficult. So let's look at it. Let f of x be a third degree polynomial with real coefficients satisfying the absolute value of f of 1, f of 2, f of 3, f of 5, f of 6, and f of 7 equals 12. And we need to find the absolute value of f of 0. Now, even if you came into this lecture at, again, say an AMC 8 level, with the knowledge you've gained in this lecture, you can solve this question, even though it may seem out of your reach at the start. I'll give you guys a second to ponder it before moving on to the solution. And let's dive in. All right, from our knowledge of polynomials, we should know that the polynomial, or at least a third degree polynomial with lines at y equals 12 and y equals negative 12. Again, it should be y equals 12, negative 12, because we know the absolute value is 12. It should look something like this. This is the shape of a third degree polynomial. This is y equals 12, and this is y equals negative 12. So it should look, in general, something like this. So examining this graph, we find that f of 1 equals f of 5 equals f of 6, while f of 2 equals f of 3 equals f of 7. Now, if you don't quite get how we got that, remember that the roots were 1, 2, 3, 5, 6, 7. So that means that this needs to be 1, this needs to be 2, this needs to be 3, this needs to be 4, this needs to be 5, and this needs to be 5, this needs to be 5, this needs to be 6, and this needs to be 7. So 1, 5, and 6 should be the same, while 2, 3, and 7 should also be the same. So let's again set up f of x as a polynomial where it's ax to the third plus bx squared plus cx plus d. And let's, without loss of generality, let's let f of 1 be negative 12. So all of these are negative 12, and f of 2 be 12. Then we can set up a system of equation, like if we plug in 1 for x, f of 1 equals a plus b plus c plus d equals negative 12. And f of 2, if we just plug in 2 into this equation, 8a plus 4b plus 2c plus d equals 12. So we can set up a system of equation using any of these 6 numbers to solve for d, which is what we're looking for, since we're looking for the absolute value of f of 0. So really, the conclusion I want to get to is that algebra is one of the most common fundamental elements of competition math, but it has an extremely wide range of difficulty. So master the basics first. Develop a natural sense of how to solve these questions through practice. And before long, knowing some basic tactics will help you solve extremely hard questions that come up in the latter portions of tests like the AIME. Hopefully you guys learned a lot from this lecture and you guys can apply these skills in your own problem solving. Thank you.